Welcome back. This is section 11.11 on nuclear medicine. Our goals in this section are to be familiar with the basic principles behind the use of radionuclides in diagnostic and therapeutic nuclear medicine. So nuclear medicine is the field of medicine in which radionuclides are used for diagnostic or imaging purposes and for therapeutic or treatment purposes. So the selection criteria for radionuclides that are appropriate to use in medical use include that at low concentrations, the radionuclide must be detectable by the instrumentation placed outside the body. So if medical provider is going to be using a radionuclide to do something like detect a region that may have cancer growth, or to even focus a radionuclide in a certain spot to get rid of cancer growth, the radionuclide needs to be detectable. They have to know where it's at and be able to detect it at very low concentrations using equipment that's placed outside the body. You want the radionuclide to have a short half-life so that it decays quickly to a more stable state. You wouldn't want to use a radionuclide that has a very long half-life, because then it would take it a very long time with very long half-lives to reach a stable state. And so you want a radionuclide that you can utilize, image right away, and then it will quickly decay into a stable product that's not going to cause any ionization damage. The radionuclide must have a known mechanism for elimination from the body. So a lot of times radionuclides are chosen that are water soluble so that they can be eliminated through the body through the urine. And then the chemical properties of the radionuclide must be such that it's compatible with normal body chemistry. You want a radionuclide, of course, that's not going to interfere in a negative way with normal body chemistry. You want one that's going to be able to either not have any effect or have a positive effect on normal body chemistry. So the most used radionuclide in medicine is called technetium-99. Its half-life is 6 hours, which is appropriate for medical imaging. So if technetium-99 is used, it'll stick around for 6 hours, and then within 6 hours, or about 6 hours later, half of it will have been decayed. Another 6 hours will pass, and at that point, 75% of it has decayed. Within then, let's see, 18 hours, you only have 1/16 left at that point, and so forth and so forth. So the half-life is appropriate. 6 hours is long enough to get a nice image taken, but not so long that the radionuclide is going to remain present and in its unstable state in the human body for too long. Technetium-99 is also a pure gamma ray emitter. It doesn't emit any alpha or beta rays, which is also advantageous for using in medicine, because we know that alpha rays, as well as beta rays to a lesser extent, can cause ionizing chemical reactions. And so with a pure gamma ray emitter, gamma rays have a very, very low ionization ability. And so you can hopefully avoid any of those formations of ion pairs and free radicals if you have a pure gamma ray emitter. So nuclear imaging is when a radionuclide tracer is used to emit a signal from a specific area of the body for diagnostic purposes. So to detect something or to observe something. So the radionuclide is often attached to a molecule that's going to migrate to the area of interest. So for example, gallium-67 will migrate to sites of infection. And so it's oftentimes used to localize or image sites of infection in people. Thallium-201 will naturally migrate to areas of impaired heart muscle, so that can be used to image if somebody has a damaged heart tissue. Sodium can show impaired circulation. Sodium is readily soluble in the blood. We know we have sodium ions circulating around. And so sodium-24 is a gamma emitter of sodium that we can use to image kind of blood flow and see if there's impaired circulation anywhere. Iodine-123 is used to image thyroid activity. It will migrate to the thyroid, so scientists and doctors can image the thyroids. And then iodine-131 or technetium-99, those are used to image tumor size and shape. And the signal is captured and turned into an image using like a PET CT scan or a SPECT CT scan. So this is an example of a whole body PET scan used to detect thyroid cancer using iodine-123. So iodine-123 is administered by IV, and then it's selectively absorbed by the thyroid at a rate that's related to the activity of the thyroid gland. So if the iodine 123 accumulation rate is higher than normal, it suggests that you have like a hyperthyroid condition or an overactive thyroid or thyroid cancer. So in this image, I put red arrows to show kind of the dark spots or the accumulation in the thyroid. And then based on how quickly iodine 123 accumulates in the thyroid, it can give doctors and scientists an idea of if that thyroid is behaving within normal ranges, or if you have a hyperactive thyroid or potentially cancer cells growing there, which would, because cancer cells grow and divide very, very rapidly, kind of out of control, they're going to accumulate that iodine 123 faster than a normal cell would. It's also normal for iodine 123 to accumulate in the stomach and the bladder, and eventually it'll accumulate in the bladder and then be excreted in the urine. Another example, this is on the left, a normal whole body, what's called fusion MRI PET scan. So a fusion scan means that they take two different types of scans, an MRI and a PET scan, and they fuse them together and color code them. So this is a normal one on the left, and this is an abnormal one on the right, showing the buildup of tracer molecules that can indicate cancer cell growth. So in this case, the radionuclide FDG18 was used. And what this radionuclide is it is a glucose-like molecule with the fluorine-18 radionucleide integrated into the molecule. And so our bodies know how to handle glucose. So it meets the criteria of kind of being something that is normal for our body's chemistry. But it has this radionuclide fluorine-18 atom integrated into the glucose, kind of like attached to it, so that wherever the glucose goes, this fluorine-18 that's going to be a gamma emitter also goes. And because glucose is kind of the sugar that's rapidly consumed by cells in order to produce energy, and cancer cells grow faster than other cell types, the accumulation of this radionuclide can suggest areas or pinpoint areas where you have cells that are growing abnormally fast as a way to diagnose cancers and figure out what's going on inside the body. This is a 3D one. Like I told you, I think this stuff is so cool. So I like to show a lot of images. This is a whole body PET scan, again, using the FDG, so fluorine-18 integrated into a glucose molecule. And glucose will accumulate in cells that are rapidly growing and rapidly reproducing. And so if you have abnormal glucose metabolism, that could be an indicator of potentially cancerous cells. So in this kind of spinning 3D diagram, you can see the red areas show kind of abnormal accumulation in the brain and kidneys. And then you get accumulation eventually of this radionuclide in the bladder because it will eventually be excreted, eliminated in the urine. Okay, so that's nuclear imaging, which is used for diagnostic purposes to locate sites of interest. Nuclear therapy is the other way that radionuclides are used. So in nuclear therapy, a radionuclide is selectively used to damage abnormal cells within the body. So in imaging, we use a radionuclide to just make an area of interest show up on a scan. In nuclear therapy, we're going to use radionuclides to selectively damage abnormal cells to get rid of them. And so what's used are radionuclides that emit radioactive particles to cause extensive damage in a select small area of abnormal cell growth. So ways that this is done is gamma rays from cobalt-60 are selectively focused into, for example, a part of the brain to selectively and very precisely destroy tumor and cancer cells by exposing them to high levels of gamma rays. We know that low levels of gamma rays, because gamma rays don't provide much ionization, they're not going to cause much damage, but when the gamma rays are focused in very, very high quantities into a very small area, that's when they can start to cause damage to selectively kill cells that medical professionals decide it's worth it to kill in order to stop the growth of a cancerous area. They can also implant alpha or beta particle emitters like yttrium-90 for the localized destruction of abnormal cells. So they could implant a small emitter in a very specific area to emit a small amount of radiation to selectively kill cells just in that area. The gamma knife, if anybody has heard of that, it's a type of radiosurgery. So surgery using radionuclides, where they use specialized equipment to focus about 200 tiny beams, and might even be more at this point. I did the research on this about 2 years ago. But they focus beams of gamma radiation onto a tumor or other target with sub-millimeter accuracy. So it's very, very, very precise. Beams of gamma radiation are focused just on the area where they want to selectively kill some cells. And so although each individual beam has little, like no effect on the brain tissue it passes through, the spot where they're all focused will have enough gamma radiation, a strong enough dose, where it can eliminate the cells in that area. So let's do a quick concept check on nuclear medicine. The area of nuclear medicine that uses radioactive nuclides and radiation to destroy abnormal cells is called what? So when we want to destroy abnormal cells by focusing radioactive nuclides on a specific spot, is it called nuclear imaging? Is it called nuclear therapy, nuclear transfusion, or none of the above? No correct answer. Well, it's not imaging. Imaging is when we use a low-level gamma emitter to selectively target an area of the body and image it, but we're not trying to kill cells in nuclear imaging, not trying to destroy abnormal cells, so it's not going to be that one. And then nuclear therapy is the correct answer. That's when you're using radionuclides and focusing them, like with a gamma knife, focusing them very specifically and very precisely into one area of the body to destroy abnormal cells. Okay, so next section, it's 11.12. We'll talk about nuclear fission and nuclear fusion reactions. I'll see you then. Thanks.